carbonyls in thiocarbonyls, or basically use this that I didn't recommend to use in the laboratory, but because the smell is very bad. But if we add H2S to this compound, what we will get is the thiophene. Okay? Right? Okay. Next one. The next one, basically, we have to synthesize an indole. We have this indole. And we start from this ketone. Okay, well, remember how we do the recrosynthesis of the indoles? Basically, we break in this way. This has to come from the hydrazine plus this ketone. That is just the ketone that we have here. Means the forward synthesis we add the ketone. First step, we will form the iminium, imine, formally is a hydrazone. Okay. Then the automerization imine enamine. And here we don't have to care because both enamines are symmetrical, that means that are the same. This sigma tropic free. Okay, and what we get is whoops. Okay, we regain the aromaticity here. Then intramolecular attack to form the hemiaminal, the aminal. Okay, we protonate this amine in order to make a very good leaving group. And this leaving group eliminates, the ammonia eliminates, and what we generate is this iminium. Okay, tautomerization iminium enamine to get the final compound. Tautomerization between this imine and this enamine to this enamine, and what we will form is the final compound. Okay? Okay, next one. We have a similar reaction, but now this time what we get as a starting material is the hydrazine. Again, we will do exactly the same than before. We will do the representative of this. Remember, we're separating these two things, and the representative has to be between this hydrazine, that is what we have, plus this ketone. Okay, 1, 2, 1, 2, 1, 2, 3, 1, 2, 3. But now the problem is that in this case the ketone is not symmetrical. That means when we will do the enamine in the key step that I showed you before, we will have two options. This is never good. That means when we are trying to do this, what we will do is simply use this aldehyde. Okay? And then we will introduce this ethyl here by another way. Okay, we do the same. I will do it fast now. You have the reaction, the mechanisms in the few minutes ago, in the last exercise. And what we will have is, I will only put the key steps. Okay, formation of the imine. This will lead to the enamine. Free, and what we will get after the cyclization, the free sigma group rearrangement, and everything. What is happening is that we will get this indole. Now we have to put an ethyl in this position. What we will do is basically, first we need to protect this nitrogen. We add butyl lithium and Boc anhydride. What we do is to put here the Boc. And now the next butyl lithium will deprotonate this position, that is the most acidic. Okay, and we can add ethyl iodide to form adding the ethyl at this position, and then the only that we need to do is to add TFA in order to get the final product. TFA to reprotect the Boc indole, to put only the indole. Okay, here is a typical example of what we need to do when we are doing the reconnection of, or a recrosynthesis of the indole, and we have a ketone that is not symmetric. What we have to do is to work with the aldehyde and then add this part by deprotonation, taking in account that we have to protect the indole before. Okay, next one. This compound and we start with this one, this ketone. Okay, remember, if we do this reaction, basically, what we need to do is, the recrosynthesis basically is this, and we have this is the recrosynthesis, the normal recrosynthesis, and then we can break this amide, and this is easy to synthesize from here. What we need to do basically is to put a amine in the alpha position. How we can do it? Well, the easy way is to do a Hellborg-Helsedinsky, that means bromine, acetic acid. What we obtain is a bromine in the alpha position. Then we add sodium azide. Okay, azide will do substitution of the bromine, hydrogen over palladium carbon, and what we get is the amine. Okay, remember, don't use lithium aluminum hydride, because if you are using lithium aluminum hydride, you will reduce azide, but also you will reduce the carbonyl compound. I mean, be careful, you have to use one thing that reduced the azide to amine, but didn't react with the carbonyl compound. Then basically we add the acyl chloride with pyridine. Here you can use the acid and a coupling reagent, up to you. In this case I prefer to use and for the final step, ammonia, and what we will get is the final product. Okay? Next one, we have to synthesize this. From okay. Well, the easiest thing will be we start from here. We add LDA, we deprotonate the alpha position to the ketone, and then we add the aldehyde, and what we will get is the aldyl product. Then this can be oxidized. For example, with manganese oxide, probably will work. And what we get is the one free decarbonyl compound that we need in order to do a reaction. This will react with hydrazine. Okay, here we don't have to take care which carbonyl will be attacked first. We don't care, because basically are two nitrogen, that means the order will not alter the product. Oops. Okay, we can form the D mean, and then basically we can make it automatic by tautomization of one of the means in enamine. And basically now the only that we need to do is do the bromination, bromine, iron clay bromide, and the bromination will take place in the active ring that always will be the 5-member ring in the only position that is available. Okay? Right? Okay. Next reaction, next exercise is basically synthesize the following compound. Okay, remember this is a pyridine. Okay, what we can do with this pyridine is the regular synthesis. Normally, first step always that we have a 6-member ring, a pyridine, isoquinoline is to form the dihydropyridine. Okay. Okay, this dihydropyridine, and then this basically is 2 enamines. Can be broken, and what we get is that this is coming from the 1 5-decarbonyl compound. How to synthesize this 1 5-decarbonyl compound? Normally we do a Michael addition. Okay, and this is okay. Well, we start from here. We use LDA at -78. Why? Because I want to do the kinetic enolate. I want to do the enolate only here. Okay, for this I need a strong base, bulky base, and low temperature. And when I have the enolate, 2 I add the Michael acceptor, and I will get one 3-decarbonyl compound. I add ammonium acetate or ammonia in acid media, and I form the imine in one side, tautomization imine enamine, and then I form the imine in the other side, tautomization imine enamine, and what I get is the dihydropyridine. Once I have the dihydropyridine, I oxidize, for example, with DDQ, and I get the final product. Okay? Next one. synthesize this pyridine. Okay, again, how I do it. The first connection or the first step in order to do a record synthesis of the pyridines is always transform the pyridine in a dihydropyridine. Then basically we can do this from a Michael addition, and this is coming from this is coming, we can break this. This is coming from, whoops. Okay, I'm breaking this enamine, that basically is the addition of amine to a carbonyl group, and then I can break this, and this will be a Michael addition. Sorry, I am changing methyl for ethyl all the time. Okay. Okay, and this can come from the addition of the ketoester to the formaldehyde. Okay? How is working this? Basically, okay, the ketoester, we add the aldehyde, in this case formaldehyde, and aldo reaction with the aeration, and what we get is the conjugated ketoester. Okay, and then we add another molecule of the ketoester with ammonia, more than ammonia, ammonium acetate. What we will form is the iminium, and then tautomerization to enamine, Michael addition, that means we will form, we will form this compound with the addition of ammonium acetate to the ketoester, Michael addition, okay, and then imine formation to generate, after tautomerization, the dihydropyridine, that we can oxidize with DDQ to get the final product. Okay? Right? The next one, basically the only that we change is that here we put a phenyl. That means that we are doing exactly the same reaction, but instead